Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in this lecture, that is symbols, alphabets and strings, we are going to understand the building blocks of ToC. So without any further delay, let's see all the topics of this lecture. Our first topic is symbols. Our second topic is alphabets. And the third and the last topic is strings. So let's start with our very first topic, that is symbols. Now here you can see that understanding symbols is the very first step in understanding theory of computation. Symbol is the most fundamental unit of ToC. Without understanding symbol, we cannot move further and we cannot understand alphabets, strings, languages and grammars. So let's get started with our discussion on symbols. Symbol is the smallest unit in theory of computation. As I have already told you, a symbol is the most fundamental unit of ToC. It cannot be divided into more smaller units. Let's see the second point. Symbol can be any letter, number, a special character, or even a pictogram, which means that we can represent symbol by any letter, any number, any special character, or even a pictogram. Now, letter, number, and special character you already know. But what is pictogram? Pictogram is the pictorial representation of any real-world entity. Now we will see some examples of symbols. So these are all the examples of symbols. If I take lowercase a, lowercase b, uppercase a, uppercase b, and uppercase z, these all are the examples of symbols as letters. Number 8, number 9, 0, 1, even 5, 6, 7, all are examples of symbols as numbers. Dollar, percentage, plus, and even minus, multiply, at the rate, hash. These all are examples of symbols as special characters. And these two are the examples of symbols as pictograms. This is the pictorial representation of a real star. It is not to be confused with the asterisk symbol that you have on your keyboard, because that comes under the special characters. And this is a pictogram of a real human being. So I hope you have understood what are symbols. And in this way, we have completed our very first topic, that is symbols. Now we will proceed to the second topic, that is alphabets. Alphabet is a finite and non-empty set of symbols. It means that alphabet is a set of symbols and that set should be finite as well as non-empty set. Now what is finite and non-empty set? Finite set is a set that contains finite or limited number of elements. We cannot have infinite number of elements in a finite set. And what is non-empty set? Non-empty set is a set that is not empty. It must contain at least one element. So, an alphabet is a finite as well as non-empty set of symbols. Let's see the second point. Alphabet is represented by sigma. It means we can represent this set of symbols or an alphabet by using a Greek letter that is called as sigma. Now let's see a few examples of alphabets. But as we all know, an alphabet is a set of symbols. So first of all, we will have some symbols. And now we will create the set of these symbols, that is an alphabet. So if I take these two symbols that are 0 and 1, I will get an alphabet sigma is equal to 0, 1, which will be called as a binary alphabet. Why binary? Because this set contains only two numbers and these are called as binary numbers, 0 and 1. If I take uppercase A, uppercase B and uppercase C, this will form a set sigma is equals to A, B, C, which is called as an uppercase alphabet. Similarly, if I take P, Q, R, all lowercase symbols, it will create a set sigma is equals to PQR, which will be called as a lowercase alphabet. But it is not always necessary that your alphabet will have a special name like uppercase or lowercase or binary. An alphabet can be the set of random symbols also. Like, if I take 0 from here, uppercase A from here, and lowercase p from here, and I will create a set of these three symbols, I will also get an alphabet. But this alphabet does not have any special name like binary or uppercase or lowercase, because symbols in this alphabet do not belong to any special type. So these all are the examples of alphabet. I hope you have understood what are alphabets. And in this way, we are done with our second topic, that is alphabets. Now we will proceed to our last topic, that is strings. A string is a finite sequence of symbols from the alphabet, which means that a string is a finite sequence of the symbols from the set of symbols, that is alphabet. So we have the alphabet, we have the symbols from the alphabet, and now we have to create the finite sequence of those symbols. But what is finite sequence? Finite sequence is the sequence of finite number of symbols. That means you cannot have infinite number of symbols to generate a string. Now let's understand strings with an example. So here we have binary alphabet. That is an alphabet containing 0 and 1. So what are the symbols of this alphabet? So this alphabet has two symbols, 0 and 1. Now we have to create the finite sequence of the symbols from the alphabet. Now if I ask you, if I take only this single 0, is this a valid string? Yes, of course. This single 0 is also a finite sequence of symbols. That is why this is a valid string. Similarly, if I take this 1, this will also be a valid string. If I take this 0 two times, this will also be a valid string. And if I take 1 0 and 1 1, this will also form a valid string. And if I reverse the order of these two symbols, I will get 1 0, which will also be a valid string. And if I take this 1 two times, this will also generate a valid string. And we can even generate longer strings. Like, if I take this 0 three times, I will get 0 0 0, which is also a finite sequence of symbols. That is a string. So similarly, I can generate all these strings. And continuing this process, we can generate even further longer strings. Now, what if I ask you that while creating a string, I take neither 0 nor 1 from these symbols? Will that generate a string? Or is it even allowed? Yes, and this will generate a string which is called as empty string or null string. We will explore more about empty string later. So in this way, we have generated multiple strings over the alphabet. Sigma is equal to 0, 1. So in this way, we have understood what are strings. Now here you need to note one important point, that while generating these strings, you can use these symbols in any order. And you can even use these symbols any number of times. And we can also calculate the length of these strings. Now, what is the length of the string? Length of the string means how many symbols are present in that string. If we talk about these two strings, these have only one symbol. That is why the length of these two strings will be 1. Similarly, the length of these all strings will be 2, because each of these strings contains only 2 symbols. The length of these strings will be 3, and the length of these strings will be 4. So, the length of the string is defined as the number of symbols in a string. That means we just need to count the number of symbols in order to calculate the length of the string. Length of a string, W, is denoted by mod of W. If we are representing our string using the letter W, its length will be denoted by mod of W. For an example, we have a string W is equal to ABA BBB. We need to calculate the length of this string. Now, we need to count the number of symbols in this string. 1, 2, 3, 4, 5, 6. That is why the length of this string mod W is equal to 6. Similarly, if I take another example, W is equal to 0, 1, 0, 1, 0, 0, 0, 1, 1. After counting the number of symbols in this string, we get modulus of W is equal to 9. That is why the length of this string W is equal to 9. Now, can you tell me the alphabet corresponding to this string? This string is only made up of two symbols, that are A and B. So the alphabet will be sigma is equal to A comma B. Similarly, this string is made up of only zeros and ones. That is why the alphabet for this string will be our binary alphabet. Sigma is equal to 0, 1. Let's see the next point. If there is no symbol in the string, it is called an empty string. As I have already told you that if I take neither of the symbols from the alphabet to generate a string, that string will be called as an empty string or null string. It is denoted by the Greek letters epsilon or lambda. And what will be the length of the empty string? Obviously 0, because empty string does not contain any symbol. So, modulus of epsilon or modulus of lambda will be equal to 0. So in this way, we have understood how to calculate the length of a string. Now we will move towards the next subtopic under strings, that is the powers of sigma. Now, to understand what are powers of sigma, we first need to take a quick recap of what we have understood in strings. So there we have taken a simple example of binary alphabet and we have generated multiple strings from these symbols. Now, what is the length of these two strings? It is 1. So if I create a set of only these two strings, that are the strings of length 1, I will get a set which is called as sigma to the power 1. Now 1 means that the set only contains the strings of length 1. Similarly, these 4 strings have length equal to 2. And if I create a set of these 4 strings, the set will be called as sigma to the power 2. And 2 represents that in the set, all the strings have length equal to 2. Similarly, the set of all these strings will be called as sigma to the power 3. And the set of all these strings will be called as sigma to the power 4. And in similar way, we can calculate sigma to the power 5, sigma to the power 6, and so on. Now, what is sigma to the power 0? It is simply the set of strings containing the strings of length 0. Now we know that there is only one string of length 0, that is epsilon or null string. So the set of only the string epsilon will be called as sigma to the power 0. Now you are all set to understand formally what are powers of sigma. Sigma to the power 0, as I have told you, is the set of all strings of length 0 over the given alphabet. Similarly, sigma to the power 1 means the set of all strings of length 1 over the given alphabet, sigma. Sigma to the power 2 means the set of all strings of length 2 over sigma. And if I generalize it, it will look like sigma to the power n is equal to set of all strings of length n over the given alphabet. Now let's take an example to understand this. That is, sigma equals 0, 1, our binary alphabet. Now what will be sigma to the power 0? It will be the set of only epsilon, the string of length 0. Sigma to the power 1 equal to 0, 1, strings of length 1. Sigma to the power 2 contains all the strings of length 2. Similarly, sigma to the power 3 will contain all the strings of length 3. And in the same way, we can calculate other powers of sigma as well, like sigma to the power of 4, power of 5, power of 6, and so on. In this way, we have understood our topic, powers of sigma. Now, what if I create a set of all these strings? That are the strings of length 0, strings of length 1, strings of length 2, length 3, length 4, and so on. That means I'm trying to create a set by taking the union of all the powers of sigma. Then that set will be called as Kleen star closure, which will be represented by sigma to the power star. So it is defined as the set of all possible strings of all the lengths. That means we are creating a set containing all the possible strings of all the lengths, length 0, length 1, length 2, and so on, over a given alphabet, sigma, including the null string. That means we are also including the strings of length 0, that is epsilon. And Kleen star closure is equal to the union of all the powers of sigma, that is sigma to the power 0, union sigma to the power 1, union sigma to the power 2, and so on, up to sigma to the power infinity. And that is why it is going to be an infinite set. Now let's take an example. Sigma is equal to 0, 1. That is our binary alphabet. So Kleen star closure is equal to the set of all strings of all possible lengths. We have the strings of length 0, strings of length 1, strings of length 2, strings of length 3, length 4, and so on. So it will be the Kleen star closure. Now I hope that you have understood what is Kleen star closure. Now, what if I remove epsilon from this set? Then we will simply get a new set. And that set without this null string epsilon is called as Kleen positive closure, represented by sigma to the power plus. So it is defined as the set of all possible strings of all the lengths over an alphabet sigma, excluding the null string. Now here we are excluding the null string epsilon. In Kleen star closure, we were including the null string also. That means sigma to the power plus is equal to the union of all the powers of sigma, but here we are not including sigma to the power 0. And this also goes up to sigma to the power infinity, and that is why it is also an infinite set. And we can also say that sigma plus is equal to sigma star minus the set of null string, which means that if we subtract the null string from Kleen star closure, we will get Kleen positive closure. Now let's see the same example again. In this set, we have all the strings of all possible lengths, but here we don't have epsilon or the null string. That is why this set is called as Kleen positive closure. In this way, we have understood what is Kleen positive closure. And now we will discuss the last subtopic under strings, that is reverse of a string. Reverse of a string is obtained by writing the symbols of the string in reverse order. That means we reverse the sequence of symbols in a given string to obtain its reversed form. For an example, we have the string W is equals to ADB, and we can get the reverse of this string represented by W to the power R, where R means reverse of the string, as this. So, B will come first, D will come second, and at last A will come. So in this way, we can get the reverse of the string. Now you may find reversing a string pretty easy. But do you think computers can also reverse a string this easily? No. We have to make several arrangements to reverse a string in computers. And that we usually study in push-down automata and Turing machines. So in this way, we have completed our last topic, that is strings. So now we have come to an end of this lecture. This was all from my side for this lecture. Thank you, and I'll see you in the next lecture.